We're going to start off today by writing the component form of a vector in terms of its magnitude and direction. So far we've written a vector in terms of its horizontal and vertical component. Today we're going to learn how to identify the horizontal component in terms of the magnitude and direction, and the vertical component in terms of its magnitude and direction. So we're going to start off with an XY axis system, and I'm going to go ahead and draw a vector out in this direction here. And we're going to call that vector V, and vector V has a certain magnitude, which is denoted with the V with the lines around it, right? Kind of looks like absolute value, but it literally just means the distance of the vector, okay? What we've done so far is we've identified vector V in terms of its horizontal and vertical component. And the horizontal is how far we've gone out with the A value, and the vertical is how far we've gone up with the B value, right? So what we're going to do is we're going to learn how to identify that vector in terms of a direction, which means the angle that is made with the positive x-axis, and the magnitude of the vector, which is the length of the vector. So we're going to start off with some good old definitions that we know. We're going to use the sine of theta and cosine of theta. So what is sine of theta equal to, you guys? Y over r. Now, what is our y value here, and what's our r value? The y value is the b. And the r value corresponds to the magnitude of the vector, which is the v there, the length of v. So let's go ahead and do that with cosine as well. Cosine's definition is x over r, so we say that's a over the magnitude of v. So what we can do from here is we can multiply both sides by the magnitude of v with both of these equations and isolate b and a. So that gives us b is equal to the magnitude of v times the sine of theta, and a is equal to the magnitude of v times the cosine of theta. Well, this is how we learned how to write component form, right? And we have what a and b are equal to right now with a magnitude and a direction angle. So let's go ahead and rewrite a new definition. We can say that a is taking the spot of, or v times, magnitude of v times cosine of theta is taking the spot of a, and magnitude of v times the sine of theta is taking the spot of b. So for example 5, we are going to find vector v with direction angle 115 and magnitude 6. So first thing I'm going to do is I'm going to draw a picture as to how that might look. I'm going to figure out where 115 is going to take me, and I know that this is 90 and this is 180. So 115 will take me about right here, and so we could say that this is 115, theta 115, and the magnitude is equal to 6. Well, I can figure out what the component form is because I have the magnitude and the direction. I know that 6 times the cosine of 115 will give me the a value, and 6 times the sine of 115 will give me the b value. So let's figure out what we get here. We got 6 times the cosine of 115, so that's negative 2.5. Yeah. Negative 2.53, or we could round up, right? Negative 2.54. And then let's go ahead and do this with sine. I'm going to do a second enter, and then scroll over the cosine and hit sine, and then hit enter. So 5.44. Alright, so there's our component form given our magnitude and direction. Now you guys, what's one thing that is making you feel confident about your answer here?
Negative 2.5.
Yeah, it's in the right quadrant. You guys are all trying to say the same thing. So we have a negative horizontal component and we have a positive vertical component, which tells us it should be shooting off in this direction, right? Okay. All right, let's do the next one here. For example 6, this time around, we're given the component form of a vector, but now we want to find the magnitude and the direction of the vector. So first thing I want to do is I want to just draw the vector in the appropriate quadrant. And I have 3, 2 here, so I'm going to go out to 3, and I'm going to go up to 2. So that's vector u here. So first thing I want to do is figure out the magnitude of this vector. And that's really easy to do. I always just think that's the Pythagorean theorem, right? Make a right triangle. And you got a 3 and a 2 here. So the magnitude of u is simply the square root of 3 squared plus 2 squared, which gives us 9 plus 4, which is 13. So the magnitude of that vector is equal to the square root of 13. So I got a root 13 right there. Now I want to figure out the angle that's made here. What's the angle? I know that cosine of theta is equal to x over r. And so what I can do from here is use the inverse cosine to figure out what the angle is based off the ratio. So I can say that the inverse cosine of 3 over the square root of 13 is equal to all right, 33.7. It does. Yeah. You guys ready to do the next one? Part B? Or should I? So part B, let's go ahead and draw the vector. And we know our vector should be in the third quadrant here, or shooting off to the negative x, negative y direction. And let's go ahead and figure out what the magnitude is equal to, so I'm going to say magnitude of v is equal to the square root of, you can simply just use that component form there to find out what the magnitude is. So we got 25 plus 4 is 29. And if we think about this in terms of a right triangle, I got my horizontal components a -2, right? So we got the inverse cosine, which will give us the angle. But we know that the cosine of theta is equal to -2 over the square root of 29. So -2 divided by the square root of 29. Ooh, that's not right, is it? Well, we know that's not right because that's in this quadrant right here, right? Remember, inverse cosine restricts us between the first and the second quadrants, right? So we have to actually take this angle and subtract it from 360, and that gives us 248, which is right about here, right? 248. So we got theta is 248. 2 point. So Morgan asked, why would I use cosine? I could use sine as well. Just wanted to get that on tape. This is a good question. Recording on. You guys might have noticed that in your book, you probably saw some problems that dealt with I and J, right? It might have thrown you off just a tad bit. We didn't get to talk about it last time. The I and J unit vectors, this is just another way of representing component form. Okay. But to explain it, let's just give a little description about the I and J unit vectors. Okay. So vector I is the unit vector whose direction is along the positive x-axis. Vector J is the unit vector whose direction is along the positive y-axis. If you were to add I plus J together, you get a resulting vector like so. Remember, when we look at the addition of two vectors visually, the resulting vector is created when we take the initial point of one and connect it to the terminal point of the other. So what I'm doing here is I'm moving J over to the right here so that its initial point is right at the same position as the terminal point of I, right? You can move vectors all around and maintain their equality as long as you don't change the direction and the length, right? So the resulting vector when we add I and J is when we go from the initial of I to the terminal of J. This literally here is I plus J, right? So you guys probably saw in your book vectors represented as like some sort of scalar times I and some sort of scalar times J, right? Another way of representing this vector here would just be that we've gone out a distance of 1 on the horizontal component and we've gone up a distance of 1 on the vertical component. So when you're looking at the I and J vectors, you can relate that back to component form by just looking at the coefficient of I and J. So let me take you to this next page here. Writing a vector with I and J is just like writing with component form. Just remember that the horizontal component is next to the I and the vertical component is next to the J. All right? So if we had vector, say this is 5a plus 3j, in component form, what we're used to, that would be written as 5 comma 3. Okay? And that's it. Okay, so in section 6.2, we're looking at the dot product of vectors, but really we're using dot product in order to be able to find the angle between two vectors. That's really our end goal here today, is to look at two vectors and figure out what the angle is between those two vectors. So we're going to start off with just a definition for dot product, which is shown here. Once again, don't let this throw you off too much. These vectors here can be written with the component form a sub 1 comma b sub 1 and a sub 2 comma b sub 2. So the dot product of those two vectors is when we multiply the horizontal components and add them to the multiplication of the vertical components. Alright, you guys. Shh, shh, shh. Danny, I'm recording right now. I have evidence. I'm going to send this link to Miss Shin. All right, let's go through this example. Example 1. We want to find the dot product of the two vectors. Okay, we're just going to do one of these. So what we want to do is we want to multiply the horizontal components and add them to the multiplication of the vertical components. So let's go ahead and do that. Dot product of v and w is we got 5 times negative 3 plus negative 2 times 4. We got minus 15 minus 8, which gives us a minus 23. What's that, Danny?
I'm waiting for a phone call because my mother might be calling from the emergency room.
Okay. But what did you say before that?
I wanted to apologize.
Okay. Thank you very much, Danny. So, you guys, this section's really all about finding the angle between two vectors. I'm not expecting you guys to memorize this, but I did want to put it there just so that it's available to you if you do want to learn it. Finding the angle between two vectors, we find that angle by using the law of cosines along with the magnitudes of these different vectors. Anyway, you guys want to talk about it, you know where I am at lunch. Without further ado, let's get on to it, all right? Let's write down some definitions. I know, we're getting to them. You guys are writing down a couple definitions. Now we're going to use the definitions and do example 2. No, we're not. We're done with B and C. Yeah, it's too easy. It's all right. It's all right. So write these definitions down, you guys. So the angle between two vectors is found by taking the dot product of those two vectors, dividing by the magnitude of those two vectors multiplied, and then taking the inverse cosine of that ratio. That will give you the angle between two vectors. So, in example 2, we want to find the angle between these two vectors shown here. Actually, we're going to draw them together. I had the picture, but I figured it's better for us to draw together. So I'm going to draw the x-axis and the y-axis. And I got vector v is going to be in the third quadrant, and vector W, that's going to be in the second quadrant. So we got in the fourth quadrant, excuse me. So we got 1, 2, 3, and then 1, 2. So So what we want to do right now is figure out what's the angle between these two vectors here. Say that again, Dylan? Well, remember that the inverse cosine will give you an angle in between 0 and 180. So no. But that was a good question. All right. So let's go ahead and figure out what the dot product is of these two vectors here. We're going to multiply the horizontal components. So 3 times -1 is a -3 plus, we're going to add to -2 times +4, which gives us a -8. So the dot product of those two vectors is -11. We need to figure out what the magnitude of those two vectors is. And let's think about the right triangle here and the hypotenuse being the vector there. So we say that vector V, that would be, oh actually, yeah, we got 3 squared plus -2 squared, square root of that. And that gives us 9 plus 4, which is 13. So we have the square root of 13 times the other vector we got. The magnitude of W is equal to the square root of 17. So what we're going to do is we're going to figure out what the angle is by taking the inverse cosine of that ratio. You guys got to be careful when you're plugging this in the calculator. You could plug it in seemingly correct and then get it wrong. So let me show you how I do it, okay? What I do is I take -11 and then open parentheses down below. We got the square root of 13 times the square root of 17. And then I press enter to give that ratio. And then from there, I do the inverse cosine of that ratio. Remember, you hit second negative to put that answer in. And then hit enter, and that gives you your angle. So looks like we're at about approximately 138. So I'm going to say that angle is approximately 138. Which, that does look like it's about 138. Are we good there?
Yeah.
Okay. And we're all happy to have Morgan back. Morgan's feeling better? Yeah.